Let's say, hypothetically, that I studied all night, woke up this morning and realized I was so tired, like truly exhausted. Maybe I got up, walked straight to the kitchen, and made an entire gallon of coffee. Hypothetically. First of all, please don't do this. And second, bear with me and imagine someone did drink all that coffee at once. Sure, the caffeine would bring them bouncing off the walls, but coffee is also acidic, with a pH of about 5. Our plasma's pH is about 7.4, so we might ask, would drinking this much coffee make someone's blood too acidic if all that acid was absorbed? The answer to that question is no, or at least not to a noticeable degree. In fact, even when chemical reactions occur directly in the bloodstream and produce or use up protons, our blood pH doesn't change much. This is because our blood is buffered. No, buffered doesn't mean that our blood cells have been lifting weights. A buffer is a solution that resists changes in pH when an acid or base is added, meaning that the buffer protects other species in solution from the effects of an added acid or base. A buffer solution is made from a weak acid, HA, and its conjugate base, A-, or from a weak base, B, and that base's conjugate acid, BH+. A simpler way of saying this is that a buffer is a solution that contains a conjugate acid-base pair for a weak acid or base. Buffers are pretty dang important for life. They're vital for the proper functioning of biological systems and are highly effective at maintaining a pH within a narrow range when small to moderate quantities of base or acid are added. So let's say I just drank that gallon of coffee. Thank goodness for the buffers in my blood, and my blood pH changes a little. How do we determine the new pH? If we want to calculate the pH of a buffer system, we can use an equation called the Henderson-Hasselbalch equation. This equation summarizes the relationship between the pH, pKa, and the concentrations of acid and base in a buffer. This allows us to calculate, and often even quickly estimate, the pH changes in a buffer solution provided we know the buffering acid's pKa. In the Henderson-Hasselbalch equation, the HA represents the weak acid, A- is the conjugate base, and the pH is the overall pH of the solution. Remember that Ka is the acid equilibrium constant, so a greater concentration of dissociated protons means a greater Ka. And going a step further, just like how pH is the negative log of a hydrogen ion concentration, H, pKa is the negative log of a Ka value. Remember, the inverse relationship between Ka and pKa introduced by that negative sign mean that as Ka increases, the pKa decreases. Larger Ka, stronger acid, larger pKa, weaker acid.